Picture this. On October 4th, 1957, a metal sphere the size of a beach ball changed everything. Not just for science, not just for politics, but for every human being who's ever looked up at the night sky and wondered what's out there. That sphere was Sputnik 1, and its simple beeping signal didn't just orbit Earth. It launched humanity into the greatest adventure we've ever embarked upon. Welcome back to Timescope. I'm your host, and if you caught our last deep dive into the 30 greatest inventors that shaped our world, you know we love exploring how human ingenuity pushes boundaries. Today, we're literally shooting for the stars as we trace humanity's incredible journey from earthbound dreamers to interplanetary explorers. Chapter 1: The Spark That Lit the Fuse. But let's rewind a bit. The space race didn't begin in 1957. It began in the minds of visionaries decades earlier. Konstantin Tsiolkovsky, a Russian schoolteacher who was nearly deaf, spent his evenings in the 1890s calculating rocket equations by candlelight. Meanwhile, American Robert Goddard was building liquid-fueled rockets in his aunt's cabbage patch, earning him the nickname Moon Man from skeptical neighbors. These weren't just dreamers. They were laying the mathematical and engineering foundation for everything that would follow. Tsiolkovsky's rocket equation is still used today by NASA engineers. Goddard's rockets, though they barely reached a few hundred feet, proved that rocket propulsion could work in the vacuum of space. But it took a world war to transform these dreams into reality. When World War II erupted, both sides desperately needed better weapons. Enter Wernher von Braun, a brilliant but controversial figure whose V-2 rockets terrorized London, but also became the blueprint for the rockets that would eventually carry humans to the moon. Here's where the story gets complex and morally ambiguous. Von Braun's rockets were built using forced labor, including concentration camp prisoners. After the war, both the United States and Soviet Union scrambled to capture German rocket scientists and technology. Von Braun ended up in America, while other German experts went to the USSR. The space race was born from the ashes of warfare, carrying both humanity's highest aspirations and its darkest chapters. Chapter 2: The Beeping That Shook the World. Now, back to that October evening in 1957. While Americans were watching Leave It to Beaver and enjoying post-war prosperity, Soviet scientists were making final preparations for something unprecedented. Sergei Korolev, the mysterious chief designer whose identity was kept secret for decades, oversaw the launch of Sputnik 1. The satellite itself was elegantly simple, a polished aluminum sphere with 4 radio antennas, weighing just 183 pounds, but its impact was anything but simple. That rhythmic beeping, transmitted on frequencies that amateur radio operators worldwide could receive, announced to everyone that the space age had begun. President Eisenhower initially downplayed Sputnik, calling it one small ball in the air, but the American public was stunned. If the Soviets could put a satellite over American soil, what else could they do? Could they drop nuclear weapons from space? The era of American technological supremacy suddenly seemed fragile. The psychological impact was enormous. Lyndon Johnson later recalled looking up at Sputnik's light, crossing the Texas sky, and feeling for the first time that America might not be the world's leading nation. This wasn't just about technology. It was about national identity, about who would shape humanity's future. Within weeks, America scrambled to respond. Vanguard rocket program, dubbed Kaputnik after its spectacular explosion on the launch pad, became a national embarrassment. It wasn't until January 1958 that America successfully launched Explorer 1, discovering the Van Allen radiation belts in the process and proving that American science could still make groundbreaking discoveries. But the Soviets weren't finished. A month after Sputnik 1, they launched Sputnik 2, this time carrying a passenger. Laika, a stray dog from the streets of Moscow, became the first living creature to orbit Earth. Her mission was one way. The technology to bring her back safely didn't yet exist. Laika's sacrifice marked both a triumph of engineering and a sobering reminder of the costs of exploration. Chapter 3: Humans Dare to Leave Earth. The next logical step seemed impossible. putting a human being into the hostile environment of space and bringing them back alive. The challenges were staggering. How do you survive in a vacuum? What happens to the human body in zero gravity? How do you navigate in 3 dimensions without up or down? Both superpowers threw enormous resources at these questions. The Soviet program, shrouded in secrecy, was led by the enigmatic Korolev. The American program, operating in the harsh light of public scrutiny, faced every failure on national television. The Soviets struck first again. On April 12, 1961, Senior Lieutenant Yuri Gagarin climbed aboard Vostok 1 for a journey that would make him the most famous person on Earth. His flight lasted just 108 minutes, but those minutes changed everything. Gagarin's famous words, "I see Earth, it is so beautiful," captured the wonder that millions felt vicariously through his experience. But here's a detail often overlooked. Gagarin didn't actually land inside his spacecraft. Soviet capsules were too heavy for a soft landing with 1960s technology, so cosmonauts ejected at high altitude and parachuted separately to the ground. This detail was kept secret for years because international aviation records required pilots to land with their aircraft. America's response came 3 weeks later with Alan Shepard's suborbital flight, 15 minutes and 116 miles above Earth, hardly comparable to Gagarin's orbit, but it proved Americans could also survive in space. Shepard's flight almost didn't happen. He spent hours strapped to his rocket, while technical delays mounted, famously quipping, "Why don't you fix your little problem and light this candle?" President Kennedy, still smarting from the Bay of Pigs disaster, needed a bold gesture to restore American prestige. On May 25, 1961, he stood before Congress and made perhaps the most audacious promise in human history. "I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth." Think about that moment. America had exactly 15 minutes of human spaceflight experience, and Kennedy was promising to land on the moon within 8 years. It was either visionary leadership or magnificent folly, and nobody knew which. Chapter 4, The Dance of Titans. What followed was the most expensive, peaceful competition in human history. At its peak, NASA's budget consumed over 4% of the entire federal budget. Imagine if we spent that much on space exploration today. The Soviet program, while smaller in absolute terms, represented an even larger percentage of their economy. The early 1960s belonged to the Soviets. While Americans struggled with exploding rockets and abbreviated flights, the USSR achieved a string of firsts that seemed to demonstrate clear technological superiority. First woman in space, Valentina Tereshkova in 1963. First spacewalk, Alexei Leonov in 1965. First spacecraft to impact the moon. First to photograph its far side. First to soft land on another world. Each Soviet achievement sent shockwaves through America. How were they doing it? The answer lay partly in their willingness to take risks that would horrify modern safety officials. Soviet spacecraft had minimal backup systems, and cosmonauts trained knowing that rescue was often impossible if something went wrong. But America was learning, often the hard way. The Gemini program, designed to develop techniques needed for lunar missions, pushed the boundaries of what humans and machines could endure. Ed White's spacewalk in 1965 was a triumph, but he nearly couldn't get back inside due to his suits ballooning in the vacuum. Gemini 8 spun wildly out of control when a thruster malfunctioned, with Neil Armstrong's quick thinking preventing disaster. Then came 1967, a year that nearly ended both programs. In January, 3 American astronauts, Gus Grissom, Ed White, and Roger Chaffee, died in a launch pad fire during a routine test. The Apollo 1 tragedy revealed NASA's overconfidence and cost-cutting had created a death trap. An oxygen-rich atmosphere and flammable materials turned a minor electrical fault into an inferno. 3 months later, the Soviets faced their own catastrophe. Vladimir Komarov, piloting the maiden flight of the new Soyuz spacecraft, died when his parachute failed during re-entry. He knew the spacecraft wasn't ready. There were over 200 known problems, but launched anyway because his backup was Yuri Gagarin. and officials couldn't risk losing their greatest hero. Both programs ground to a halt for redesign and soul-searching. The space race had claimed its first casualties, and suddenly the moon seemed very far away. Chapter 5: Apollo Rising. The Apollo 1 fire was NASA's darkest hour, but it also became the catalyst for their finest achievements. The agency completely redesigned the command module, replacing the oxygen atmosphere with a nitrogen-oxygen mix, removing flammable materials, and redesigning the hatch so it could open in seconds rather than minutes. Meanwhile, the massive Saturn V rocket was taking shape. Standing 363 feet tall and weighing 6.2 million pounds when fueled, it remains the most powerful rocket to successfully carry humans into space. Each first-stage burn consumed fuel at a rate that would drain an average swimming pool in 25 seconds. The comeback began with Apollo 7 in October 1968, an Earth orbital test that proved the redesigned command module worked. But NASA had a more ambitious plan for Apollo 8. Originally intended as another Earth orbital test, mission planners made a bold decision. They would send the crew around the moon. Think about that leap of faith. Apollo 8 would be only the second crewed Apollo flight. Yet NASA was betting everything on a lunar mission. The decision was partly driven by intelligence suggesting the Soviets were preparing their own lunar flight. America couldn't afford to let the USSR achieve yet another first. On December 21, 1968, Frank Borman, Jim Lovell, and William Anders became the first humans to leave Earth's gravitational influence. Their Christmas Eve broadcast from lunar orbit, reading from the Book of Genesis while showing Earth rising over the lunar horizon, became one of the most watched television events in history. That image, Earthrise, may have been Apollo 8's greatest gift to humanity, seeing our blue, fragile planet suspended in the cosmic void gave birth to the environmental movement and forever changed how we see ourselves. As Anders later said, "We came all this way to explore the moon, and the most important thing is that we discovered the Earth." Apollo 9 tested the lunar module in Earth orbit, while Apollo 10 conducted a full dress rehearsal, flying to within 9 miles of the lunar surface. Everything was ready for the ultimate goal, landing humans on another world. But here's a question for you. If you had been alive in 1969, would you have believed humans could actually land on the moon? Drop your thoughts in the comments. I'm curious about your perspective on humanity's greatest adventure. Chapter 6: One Giant Leap. July 16, 1969. 1 million people gathered along Florida's beaches to witness Apollo 11's launch, while 600 million more watched on television, 1/6 of the world's population at the time. The crew, Neil Armstrong, Buzz Aldrin, and Michael Collins, carried the hopes and dreams of not just America, but all humanity. The journey to the moon took 3 days, but the real drama began during the lunar landing. As the Eagle descended toward the Sea of Tranquility, computer alarms blared in the cockpit. The landing computer was overloaded, struggling to process navigation data while steering the fragile craft. In mission control, 26-year-old engineer Steve Bales made the split-second decision to continue the landing despite the alarms. Armstrong took manual control with less than 30 seconds of fuel remaining, piloting over a boulder field to find smooth terrain. His pulse rate, monitored by NASA, jumped to 150 beats per minute, about what you'd expect from someone performing the most difficult landing in human history. The Eagle has landed, 4 words that announced humanity's arrival on another world. But the mission's most profound moment came hours later. As Armstrong stepped onto the lunar surface, his carefully prepared words, "That's one small step for man, one giant leap for mankind," were heard by the largest audience in human history up to that point. Though a static burst obscured the A in a man, the meaning was clear. This wasn't just an American achievement, but a human one. For 21 hours, Armstrong and Aldrin explored an alien landscape while Collins orbited overhead, perhaps the loneliest human in history. They collected rocks, planted a flag, and left a plaque reading, "Here men from the planet Earth first set foot upon the moon, July 1969 AD. We came in peace for all mankind." The return journey held its own dangers. The lunar module's ascent stage engine had to work perfectly. There was no backup plan. If it failed, Armstrong and Aldrin would be stranded forever. The engine fired flawlessly, beginning their journey home to ticker tape parades and global celebration. Apollo 11's success was so overwhelming that many people forgot 5 more lunar missions were planned. Apollo 12 proved the first landing wasn't a fluke, touching down within walking distance of the Surveyor 3 probe that had landed 2 years earlier. Chapter 7: Crisis and Triumph. Then came Apollo 13, the mission that NASA called a successful failure. On April 13, 1970, an oxygen tank explosion 200,000 miles from Earth turned a routine lunar mission into a desperate fight for survival. Jim Lovell, Fred Hayes, and Jack Swigert found themselves in a crippled spacecraft with limited power, water, and breathable air. The next 4 days became a masterclass in problem-solving under pressure. Mission Control, led by Flight Director Gene Kranz, worked around the clock to find solutions to problems no one had ever imagined. How do you remove carbon dioxide from the air when you're using the wrong type of filter? How do you navigate home when your guidance system is offline? How do you restart a spacecraft that was never designed to be shut down in space? The most famous moment came when engineers had to figure out how to fit square carbon dioxide scrubbers into round holes using only materials available on the spacecraft. As one flight controller later said, failure is not an option. Though Kranz himself never used those exact words, they captured the team's determination perfectly. Apollo 13's crew splashed down safely on April 17th, proving that NASA's investment in redundancy and human ingenuity could overcome even catastrophic failures. The mission became a symbol of American can-do spirit and the power of teamwork under pressure. The final 3 Apollo missions pushed scientific exploration to new heights. Apollo 15 introduced the lunar rover, allowing astronauts to venture miles from their landing site. Apollo 17 carried the only scientist astronaut to walk on the moon, geologist Harrison Schmitt, whose excited description of orange-colored lunar soil provided new insights into the moon's formation. On December 14, 1972, Eugene Cernan became the last human to walk on the moon, saying, "We leave as we came, and God willing, as we shall return." With peace and hope for all mankind, he couldn't have known that over 50 years later, humans still haven't returned. Chapter 8: The Space Truck Era. By the early 1970s, the space race was effectively over. America had won the ultimate prize, the moon, and public interest waned as economic problems mounted at home. The Vietnam War, oil crises, and social upheaval made expensive space missions seem like luxury America couldn't afford. NASA's answer was the Space Shuttle, conceived as a reusable space truck that would make orbit routine and affordable. The shuttle promised to reduce launch costs from $10,000 per pound to just $300 per pound. Like many promises in aerospace, it proved wildly optimistic. The first shuttle, Columbia, launched on April 12, 1981, exactly 20 years after Gagarin's flight. Commander John Young and pilot Robert Crippen rode the most complex machine ever built on what was essentially a test flight. Unlike previous spacecraft, which were tested unmanned first, the shuttle was so complicated that the only way to test it was with humans aboard. The shuttle program achieved remarkable things. It deployed and repaired the Hubble Space Telescope, built the International Space Station, and carried hundreds of astronauts from dozens of countries into orbit. Sally Ride became America's first woman in space in 1983, while Guion Bluford became the first African-American astronaut the same year. But the shuttle also highlighted the dangers of treating spaceflight as routine. On January 28, 1986, millions of schoolchildren watching on TV saw Challenger disintegrate 73 seconds after launch, killing all 7 crew members, including teacher Krista McAuliffe. The cause was prosaic, rubber O-rings that hardened in cold weather. But the investigation revealed NASA had become overconfident and complacent about safety. The shuttle fleet returned to flight after 32 months of redesign and soul-searching. But the specter of Challenger haunted every subsequent mission. Spaceflight, everyone remembered, was still dangerous. Meanwhile, the Soviet Union was writing its own chapters in space exploration. Their Mir space station, launched in 1986, became humanity's first permanent foothold in space. For 15 years, Mir hosted international crews conducting long-duration missions that pushed the boundaries of human endurance in zero gravity. Chapter 9: Robots as Pioneers. While humans captured headlines, robotic explorers were quietly revolutionizing our understanding of the solar system. The Soviet Venera program achieved the first successful planetary landing, revealing Venus as a hellish world with surface temperatures hot enough to melt lead and crushing atmospheric pressure. America's Mariner and Voyager programs transformed our view of the outer solar system. Voyager 1 and 2, launched in 1977 to take advantage of a rare planetary alignment that occurs once every 175 years, revealed the moons of Jupiter and Saturn as complex worlds in their own right. Who could have predicted that Europa might have an ocean beneath its icy surface, potentially harboring life? Or that Titan, Saturn's largest moon, would have rivers and lakes of liquid methane? These discoveries didn't just expand scientific knowledge, it expanded our concept of where life might exist. The Voyager spacecraft, now in interstellar space, carry golden records containing sounds and images from Earth, including music by Bach and Chuck Berry, greetings in 55 languages, and the sound of a human heartbeat. Carl Sagan, who led the committee that created the record, called it a message in a bottle cast into the cosmic ocean. But the most transformative robotic missions targeting Mars, our enigmatic neighbor. Early flyby missions revealed a cratered, seemingly dead world, crushing dreams of Martian civilizations. But as technology improved, so did our understanding of the red planet's complexity. Viking 1 and 2, launched in 1975, were the first American spacecraft to successfully land on Mars. Their images revealed a world of ancient riverbeds and massive volcanoes, suggesting Mars once had flowing water and might have been hospitable to life. The Viking life detection experiments produced tantalizing but inconclusive results that scientists still debate today. Here's a question that's fascinated scientists for decades. If we found microscopic life on Mars, how would that change humanity's perspective on our place in the universe? Share your thoughts in the comments. This is one of the biggest questions facing space exploration today. Chapter 10: International Cooperation in the Cosmic Frontier. The end of the Cold War transformed space exploration from competition to cooperation. The most visible symbol of this change was the International Space Station, ISS, a project that would have been unthinkable during the height of the space race. The ISS represented an extraordinary partnership between former enemies. Russian cosmonauts and American astronauts worked side by side, using technology from 16 nations to build humanity's most complex international project. The station's construction required 42 assembly missions over 13 years, with each component precisely engineered to fit together in the harsh environment of space. Living aboard the ISS pushed the boundaries of human adaptation. Astronauts learned to sleep while floating, to eat carefully to prevent food from floating away, and to exercise on specialized equipment to prevent bone loss in zero gravity. Commander Scott Kelly's year-long mission provided crucial data about the physical and psychological challenges of long-duration spaceflight, information essential for future missions to Mars. But perhaps the ISS's greatest achievement was proving that international cooperation could overcome political tensions. Even during periods of strained relations between Russia and the West, the space station continued operating seamlessly. Astronauts and cosmonauts regularly saved each other's lives, shared meals, and worked toward common goals 250 miles above the political conflicts below. The station also became a platform for groundbreaking science. In the absence of gravity, proteins can grow into more perfect crystals, potentially leading to better medicines. Flames burn differently in space, providing insights into combustion that could improve energy efficiency on Earth. Students worldwide have conducted experiments aboard the ISS, inspiring a new generation of scientists and engineers. Chapter 11: The New Space Age. The 21st century has witnessed the emergence of commercial spaceflight, fundamentally changing who can access space and how we think about space exploration. Companies like SpaceX, Blue Origin, and Virgin Galactic have turned science fiction concepts into business models. Elon Musk's SpaceX deserves particular attention for revolutionizing rocket technology. When Musk founded the company in 2002, the idea of reusable rockets was considered impossible by most aerospace experts. Rockets had always been thrown away after one use, like enormously expensive fireworks. SpaceX's breakthrough came with the Falcon 9's first successful landing in 2015. Watching a rocket booster descend through the atmosphere, reignite its engines, and land precisely on a floating platform was like watching magic. But it was actually brilliant engineering combined with modern computing power and advanced materials. This innovation slashed launch costs from $10,000 per kilogram to around $2,000 per kilogram, making space accessible to smaller nations, universities, and private companies. Suddenly, countries like South Korea and the UAE could afford sophisticated space programs. The human spaceflight revolution culminated in 2020 when SpaceX's Crew Dragon became the first commercially built spacecraft to carry astronauts to orbit. For the first time since the shuttle's retirement in 2011, America could launch its own astronauts without relying on Russian Soyuz rockets. But SpaceX wasn't alone in transforming space exploration. Jeff Bezos's Blue Origin pursued a different approach, focusing on suborbital tourism and developing massive rockets for deep space exploration. Their New Shepard vehicle has carried paying customers to the edge of space, fulfilling childhood dreams of experiencing weightlessness and seeing Earth's curvature. Virgin Galactic took yet another approach, using a unique air launch system to carry passengers to suborbital space. Richard Branson's personal flight aboard VSS Unity in 2021 demonstrated that space tourism was becoming reality, not just aspiration. Chapter 12: The Red Planet Beckons. While commercial companies transformed Earth orbit access, robotic explorers continued pushing deeper into the solar system. Mars became the focus of an international armada of sophisticated missions that have revealed the Red Planet as a complex, dynamic world with a fascinating history. NASA's Mars Pathfinder mission in 1997 introduced the world to Sojourner, a six-wheeled rover the size of a microwave oven. Its successful 83-day mission proved that mobile robots could explore planetary surfaces, paving the way for increasingly sophisticated successors. The Mars exploration rovers Spirit and Opportunity, launched in 2003 for 90-day missions, exceeded all expectations. Spirit operated for 6 years, while Opportunity continued for an incredible 15 years, traveling over 28 miles across the Martian surface. These rovers found definitive evidence that water once flowed on Mars, transforming our understanding of the planet's past. But the real game changer was Curiosity, a nuclear-powered rover the size of a small car, landing via an innovative sky crane system in 2012. Curiosity carried a sophisticated chemistry laboratory capable of analyzing Martian rocks and soil with unprecedented precision. Its discoveries confirmed that Mars once had conditions suitable for life, at least in terms of chemistry and water availability. The Perseverance rover, which landed in 2021, took Mars exploration to the next level. Not only is it searching for signs of ancient microbial life, but it's also collecting carefully selected samples for eventual return to Earth. This mission represents humanity's first serious attempt to bring pieces of another planet home for detailed analysis. Perhaps most exciting is Perseverance's companion, the Ingenuity helicopter. This tiny aircraft achieved the first powered flight on another planet, proving that aerial exploration of Mars is possible. Future missions might include swarms of helicopters exploring Martian canyons and polar regions that rovers cannot reach. China has also emerged as a major player in Mars exploration. The Tianwen-1 mission, consisting of an orbiter, lander, and rover, made China only the second country to successfully operate a rover on Mars. The Zhurong rover has provided new insights into Martian geology and weather patterns. These robotic missions are preparing for the ultimate goal, sending humans to Mars. But the challenges are staggering. A round trip to Mars takes over 2 years, exposing astronauts to dangerous levels of cosmic radiation. The psychological challenges of isolation and confinement in a small spacecraft for such a long period are unprecedented in human experience. Chapter 13: Return to the Moon. After decades of absence, humanity is preparing to return to the moon through NASA's Artemis program. Named after Apollo's twin sister, Artemis aims to establish a sustainable lunar presence rather than the brief visits of the Apollo era. The goals are ambitious. Land the first woman and next man on the moon by 2026, establish a lunar base, and use the moon as a stepping stone to Mars. Unlike Apollo, which was driven by Cold War competition, Artemis emphasizes international cooperation and commercial partnerships. The program's centerpiece is the Space Launch System, SLS, the most powerful rocket NASA has ever built. Standing 322 feet tall, SLS can send 59,500 pounds to the moon, enough for a crew capsule, lunar lander, and supplies for extended surface operations. Artemis 1, an uncrewed test flight launched in 2022, successfully demonstrated the SLS rocket and Orion spacecraft by completing a lunar flyby mission. The flight tested crucial systems, including heat shields designed to protect astronauts during high-speed re-entry from the moon. But Artemis represents more than just returning to familiar territory. The program plans to establish a lunar gateway, a small space station in lunar orbit that will serve as a staging point for surface missions. Future astronauts will be able to stay on the moon for weeks rather than days, conducting serious scientific research in the lunar South Pole region. Why the South Pole? Unlike the equatorial regions visited by Apollo, the lunar poles contain water ice in permanently shadowed craters. This ice could be converted into drinking water, breathable air, and even rocket fuel, making the moon a refueling station for deeper space exploration. The technological challenges are immense. Lunar nights last 2 weeks, with temperatures dropping to -230 degrees Fahrenheit. Equipment must survive these extreme conditions while operating reliably for months or years. Lunar dust, finer than talcum powder and electrostatically charged, gets into everything and poses serious health risks. Chapter 14: Private Pioneers and Space Billionaires. The commercialization of space has created a new breed of space pioneers, entrepreneurs who see the final frontier as the ultimate business opportunity. These space billionaires have invested their personal fortunes in ventures that government agencies deemed too risky or expensive. Elon Musk's vision for SpaceX goes far beyond launching satellites and astronauts. His ultimate goal is making humanity a multiplanetary species by establishing a self-sustaining city on Mars. The company's Starship, currently in development, is designed to carry 100 people to Mars and return to Earth for reuse. This isn't just billionaire fantasy. SpaceX has demonstrated remarkable technical achievements. The company has successfully landed and reused rocket boosters dozens of times, something experts once considered impossible. Their Crew Dragon spacecraft has become NASA's primary means of reaching the International Space Station. Jeff Bezos approaches space differently through Blue Origin, focusing on developing space infrastructure for future generations. His vision includes millions of people working in space, with heavy industry moved off Earth to preserve our planet's environment. Blue Origin's New Glenn rocket, when operational, will compete directly with SpaceX for satellite launches and deep space missions. Richard Branson's Virgin Galactic has pioneered space tourism, offering paying customers a few minutes of weightlessness and spectacular views of Earth's curvature. While critics dismiss this as a rich person's joyride, supporters argue that space tourism is following the same path as aviation, starting with wealthy adventurers before becoming accessible to ordinary people. These commercial ventures have achieved something government programs struggled with: making space exploration profitable. By reducing launch costs and increasing mission frequency, private companies have made space accessible to smaller organizations and countries that couldn't afford their own space programs. But commercialization has also raised important questions. Who owns space resources? How do we prevent the weaponization of space? What happens when commercial interests conflict with scientific exploration or environmental protection? Chapter 15. The search for life beyond Earth. Perhaps the most profound question driving space exploration is whether Earth is unique in harboring life. This search has evolved from science fiction speculation to serious scientific endeavor, with space missions specifically designed to detect signs of life on other worlds. The discovery of extremophiles on Earth, organisms that thrive in conditions previously thought impossible for life, has revolutionized our understanding of life's possibilities. Scientists have found bacteria living in boiling water, surviving in radioactive environments, and thriving without sunlight in deep ocean vents. If life can exist in such extreme conditions on Earth, perhaps it can survive in the harsh environments of other worlds. Mars remains the primary target in the search for life. The planet clearly had water in its past, with evidence of ancient lakes, rivers, and possibly even oceans. The Perseverance rover is actively searching for biosignatures, chemical or physical evidence that life once existed on Mars. But Mars isn't the only candidate for harboring life. Europa, one of Jupiter's moons, likely contains more liquid water than all Earth's oceans combined beneath its icy surface. NASA's upcoming Europa Clipper mission will conduct detailed reconnaissance of this mysterious moon, searching for plumes of water vapor that might contain organic compounds. Saturn's moon Enceladus has already surprised scientists by ejecting water vapor and organic molecules from its south pole. The Cassini spacecraft flew through these plumes and detected complex organic compounds, suggesting that Enceladus might have the chemical ingredients necessary for life. Even more intriguingly, Saturn's largest moon, Titan, has rivers, lakes, and rain, though they're composed of liquid methane rather than water. Some scientists speculate that Titan might host exotic forms of life based on completely different chemistry than Earth life. The search for life extends beyond our solar system through the study of exoplanets, worlds orbiting other stars. The Kepler Space Telescope and its successors have discovered thousands of exoplanets, including some in the habitable zone, where liquid water could exist on their surfaces. The James Webb Space Telescope, launched in 2021, can analyze the atmospheres of some exoplanets, searching for gases that might indicate biological activity. Oxygen, methane, and water vapor in an exoplanet's atmosphere could be signs of life, though distinguishing biological signatures from geological processes remains challenging. Here's a thought experiment for you. If we discovered definitive proof of life on another world, even just microbes, how do you think it would change human society, religion, and philosophy? This discovery might be just decades away. What are your thoughts on how humanity would react? Chapter 16. The challenges ahead. As we stand on the threshold of becoming a spacefaring civilization, we face unprecedented challenges that will test human ingenuity, cooperation, and wisdom. These aren't just technical problems. They're fundamental questions about humanity's future and our responsibilities as cosmic citizens. The physiological challenges of long-duration spaceflight remain largely unsolved. Astronauts lose bone density, muscle mass, and experience vision problems during extended missions. The psychological challenges may be even greater. Imagine being confined with the same small group of people for 2.5 years on a Mars mission, knowing that Earth is just a small blue dot in the sky. Radiation exposure presents another serious obstacle. Earth's magnetic field and atmosphere protect us from cosmic radiation and solar particles, but spacecraft and planetary surfaces offer little protection. A single large solar flare could deliver a lethal dose of radiation to unprotected astronauts. The engineering challenges are equally daunting. Spacecraft must operate reliably for years without maintenance, using only the spare parts they carry. Everything must work perfectly the first time. There's no calling for help when you're millions of miles from Earth. But perhaps the greatest challenges are societal and political. Space exploration requires international cooperation on an unprecedented scale. But terrestrial conflicts and nationalism continue to complicate these efforts. The militarization of space is an ever-present threat, with nations developing anti-satellite weapons and cyber warfare capabilities. Environmental concerns are also emerging as space activities increase. Low Earth orbit is becoming cluttered with debris from decades of space missions, creating hazards for current and future spacecraft. The Kessler syndrome, a cascade of collisions that could make orbital space unusable, is no longer just a theoretical concern. Commercial space ventures raise questions about equity and access. Will space become the exclusive domain of wealthy nations and billionaire entrepreneurs? Or can the benefits of space exploration be shared more broadly? How do we balance profit motives with scientific exploration and environmental protection? Chapter 17. Breakthrough technologies on the horizon. The next phase of space exploration will be enabled by revolutionary technologies that are moving from science fiction to engineering reality. These innovations promise to make space travel faster, safer, and more affordable than ever before. Nuclear propulsion represents one of the most promising breakthroughs. While chemical rockets have carried us this far, they're fundamentally limited by the energy available in chemical bonds. Nuclear thermal and nuclear electric propulsion systems could cut travel time to Mars from 9 months to just 3 months, dramatically reducing radiation exposure and psychological stress on crews. NASA's Draco program aims to demonstrate nuclear thermal propulsion in space by 2027. These engines heat propellant using nuclear reactors instead of chemical combustion, providing twice the efficiency of conventional rockets. For Mars missions, this could mean the difference between the risky 2.5-year journey and a manageable 6-month round trip. Even more exotic propulsion concepts are under development. Solar sails use the pressure of sunlight for propulsion, requiring no fuel, but capable of achieving incredible speeds over time. Japan's Icaros probe successfully demonstrated solar sailing in 2010, and future missions might use massive solar sails to reach nearby stars. Ion drives, which accelerate charged particles to extremely high speeds, are already powering deep space missions. NASA's Dawn spacecraft used ion propulsion to visit both the asteroid Vesta and dwarf planet Ceres, something impossible with chemical rockets. Future ion drives might be powered by nuclear reactors, providing the electricity needed for high-thrust operations. Breakthrough Starshot, funded by tech billionaire Yuri Noner, proposes using powerful ground-based lasers to accelerate tiny spacecraft to 20% of light speed. These light sails could reach the nearest stars in just 20 years, potentially sending back humanity's first images of exoplanets. In situ resource utilization, ISRU, using local materials rather than shipping everything from Earth, will be crucial for sustainable space exploration. NASA's MOXIE experiment aboard the Perseverance rover has successfully converted Martian carbon dioxide into oxygen, proving that future Mars missions could produce their own breathing air and rocket fuel. 3D printing technology is revolutionizing how we think about space construction. Instead of manufacturing components on Earth and shipping them at enormous cost, future missions might print tools, spare parts, and even habitat structures using local materials. The ISS already has a 3D printer that has produced tools and replacement parts in orbit. Chapter 18. The economics of space. Space exploration has evolved from a purely scientific and political endeavor to a trillion-dollar economic sector that's reshaping how we think about resources, manufacturing, and human civilization's future. The satellite industry alone generates over $300 billion annually, providing services from GPS navigation to weather forecasting to global communications. Without satellites, modern life would grind to a halt. No credit card transactions, no international phone calls, no accurate weather predictions. But the real economic revolution lies in space manufacturing and resource extraction. The microgravity environment of space offers unique advantages for producing certain materials. Fiber optic cables, pharmaceuticals, and metal alloys can be manufactured in space with properties impossible to achieve on Earth. Asteroid mining represents perhaps the ultimate economic opportunity. A single metallic asteroid could contain more platinum than has ever been mined on Earth, worth trillions of dollars. Near-Earth asteroids contain enough water, rare metals, and other materials to support extensive space development without depleting Earth's resources. Companies like Planetary Resources and Deep Space Industries have begun developing the technologies needed for asteroid prospecting and extraction. While still in early stages, asteroid mining could fundamentally alter Earth's economy by making rare materials abundant and cheap. Space-based solar power offers another transformative possibility. Solar panels in space receive constant, unfiltered sunlight and could generate far more power than Earth-based installations. Japan and several other countries are investing heavily in research to beam solar power from space to Earth via microwave transmission. The emerging space tourism industry is creating entirely new economic sectors. Virgin Galactic charges $450,000 for a suborbital flight, while SpaceX has sent private citizens to orbit for tens of millions of dollars. As costs decrease, space tourism could become as common as international air travel was in the 1960s. Space hotels, manufacturing facilities, and research stations will require large permanent workforces in space. These space workers will need housing, food, entertainment, and all the services that make life worthwhile. An entire space-based economy is beginning to emerge, potentially supporting millions of people working beyond Earth. Chapter 19: The Philosophical Revolution. Space exploration has fundamentally changed how humanity sees itself and our place in the cosmos. The philosophical implications of our journey beyond Earth continue to reverberate through science, religion, and human consciousness. The overview effect, the cognitive shift astronauts experience when seeing Earth from space, has become one of the most profound psychological phenomena associated with space travel. Astronauts consistently report that seeing Earth as a small, fragile blue marble floating in the cosmic void fundamentally changes their perspective on national boundaries, environmental protection, and human unity. Edgar Mitchell, who walked on the moon during Apollo 14, described the experience as a peak moment that gave him a profound sense of universal connectedness. This perspective has inspired environmental movements, influenced spiritual thinking, and challenged traditional notions of nationalism and territorial boundaries. The search for extraterrestrial life raises profound questions about humanity's uniqueness and significance. If life exists elsewhere in the universe, even in microbial form, it would fundamentally challenge anthropocentric worldviews and force us to reconsider our place in the cosmic order. The possibility of finding intelligent alien life poses even more challenging questions. How would human religions adapt to the existence of other intelligent species? Would our concepts of morality, consciousness, and purpose need to be completely reconsidered? Space exploration has also democratized our view of the universe. When the Hubble Space Telescope revealed that the cosmos contains hundreds of billions of galaxies, each containing hundreds of billions of stars, it made clear that Earth and humanity occupy an almost infinitesimally small part of reality. Yet paradoxically, this humbling perspective has also elevated humanity's significance. As far as we know, humans are the only species capable of understanding the universe's structure, age, and evolution. We alone can contemplate our cosmic significance and take action to ensure life's continuation beyond our home planet. The concept of becoming a multiplanetary species represents a fundamental shift in human identity. For all of human history, Earth has been not just our home, but our entire universe. Establishing permanent settlements on other worlds would mark humanity's transition from a terrestrial to a cosmic species. This transition raises ethical questions about our responsibilities to other worlds and potential life forms we might encounter. Do we have the right to transform Mars into a second Earth? How do we explore other worlds without contaminating them with Earth life or destroying indigenous ecosystems that might exist? Chapter 20: Preparing for the Cosmos. As we stand at the threshold of becoming a true spacefaring civilization, the choices we make in the next few decades will determine humanity's cosmic future. The infrastructure we build, the technologies we develop, and the international frameworks we establish will shape space exploration for centuries to come. Education and public engagement remain crucial for sustaining support for space exploration. The generation that will land on Mars and establish lunar colonies is already in school today. Inspiring young people to pursue careers in science, technology, engineering, and mathematics isn't just about filling jobs. It's about preparing humanity for its cosmic destiny. Space agencies worldwide are investing in educational outreach, bringing space science into classrooms through programs like NASA's Educational Partnerships and the European Space Agency's Teacher Training Initiatives. These programs don't just teach facts about space, they inspire wonder and curiosity about the universe. International cooperation will be essential for tackling the massive challenges of interplanetary exploration. No single nation has the resources to establish permanent settlements on Mars or mount expeditions to the outer solar system. The International Space Station proved that former enemies can work together successfully in space. Now we must expand that cooperation to encompass the entire solar system. The Artemis Accords, signed by dozens of nations, represent an important step toward establishing international norms for space exploration. These agreements promote peaceful use of space, protection of heritage sites like the Apollo landing locations, and sharing of scientific data. But formal treaties may not be enough. Space exploration requires unprecedented levels of trust, cooperation, and shared commitment to common goals. Astronauts and cosmonauts have consistently reported that national boundaries seem meaningless when viewed from space. Perhaps this perspective will help humanity overcome the terrestrial conflicts that have hindered cooperation for millennia. Private companies are playing an increasingly important role in space development, but their profit motives must be balanced with broader human interests. How do we ensure that space resources benefit all humanity rather than just wealthy corporations? How do we prevent the militarization of space while allowing legitimate commercial activities? Final chapter, the infinite frontier. As we reach the end of our journey through space exploration's remarkable history, it's worth reflecting on how far we've come and contemplating the infinite possibilities that lie ahead. From Sputnik's simple beeping signals to rovers exploring Mars, from Yuri Gagarin's 108-minute flight to astronauts living in space for over a year, humanity has achieved things that would have seemed impossible just decades ago. We've walked on another world, sent robotic explorers throughout the solar system, and peered deep into cosmic history with space-based telescopes. But in many ways, we're still at the very beginning of our cosmic journey. The first human footsteps on Mars are likely just years away. Permanent settlements on the Moon and Mars will follow within decades. Within this century, humans might be born on other worlds, making them the first true citizens of the cosmos rather than just Earth. The technologies being developed today, nuclear propulsion, asteroid mining, space manufacturing, artificial intelligence, will enable exploration and settlement throughout the solar system. Future generations might think nothing of traveling between planets, mining asteroids, or vacationing on the moons of Jupiter. Looking even further ahead, the technologies needed for interstellar travel, fusion rockets, generation ships, perhaps even faster than light travel, exist at least in theoretical form. The stars that once seemed forever beyond reach might become destinations for our descendants. But space exploration isn't just about technology and adventure. It's about ensuring humanity's long-term survival and prosperity. Earth faces numerous existential risks, from asteroid impacts to climate change to potential nuclear war. Establishing self-sustaining settlements on multiple worlds provides insurance against these threats while expanding opportunities for human flourishing. The lessons we learn from space exploration continue to benefit life on Earth. Satellite technology enables global communications, weather forecasting, and navigation. Medical research conducted in microgravity leads to new treatments for diseases. Earth observation from space helps us understand and protect our planet's environment. Perhaps most importantly, space exploration expands human consciousness and inspires us to think beyond the limitations of our terrestrial existence. When we see Earth as astronauts do, a beautiful, fragile oasis of life in the cosmic void, we understand our shared humanity and common destiny. As we look toward the future, the questions facing us are no longer whether we'll explore space, but how quickly we'll do it, and whether we'll do it wisely. The universe is vast and full of wonders waiting to be discovered. The only limits are those we impose on ourselves through lack of vision, courage, or cooperation. Closing, and that brings us to the end of our cosmic journey, from a beach ball-sized satellite beeping over a divided world to rovers searching for life on Mars and spacecraft headed for the stars. But before we sign off, I want to hear from you. Throughout this exploration, we've posed several questions. Would you have believed humans could reach the moon in 1969? How do you think discovering alien life would change human society? What role do you think private companies should play in space exploration? Drop your thoughts in the comments below. These aren't just academic questions anymore. Many of you watching this will live to see humans walking on Mars, permanent lunar bases, and perhaps even the first detection of extraterrestrial life. Your generation will help decide whether humanity embraces its cosmic destiny with wisdom and unity, or allows terrestrial conflicts to limit our potential. If you found this journey through space exploration as fascinating as I did, make sure to hit that like button and subscribe to Timescope. We're just getting started on our exploration of how human ingenuity has shaped our world and our future. Speaking of shaping our world, our next deep dive takes us in a completely different direction, but one that's equally shaped human history. We'll be exploring weapons of war, from medieval battlefields to World War II and the terrifying arsenal of World War III. From the crossbows that changed medieval warfare to the atomic bombs that ended World War II, and the cyber weapons and autonomous systems that might define future conflicts, it's a journey through humanity's most destructive and, unfortunately, most innovative technologies. War has always been a terrible driver of human innovation, pushing technology forward at breakneck speed. The same rocket technology that took us to the moon started as weapons of war. The internet began as a military project. Even GPS was originally designed for nuclear submarines. Next week, we'll explore this dark but crucial aspect of human ingenuity. Until then, keep looking up, both at the stars we're destined to reach and at the remarkable story of how we learned to leave our home planet behind. The universe is waiting, and humanity's greatest adventures are still ahead of us. This has been Timescope, where we explore the technologies and discoveries that shaped our past and will define our future. Thanks for joining me on this cosmic journey. Now let's go explore the universe together.